2. Voltage ratio. In experiment 6c, we find that the induced current in the secondary coil becomes larger when the secondary coil has more turns. The following experiment investigates the relationship between the voltage ratio and the turns ratio.
We will measure the voltage ratio of a transformer and compare it with the turns ratio using a CRO. This is a simple transformer. Its primary coil has 10 turns and its secondary coil has 25 turns. Connect a 2.5 volt lamp to each of the primary and secondary coils. Apply an AC voltage of 1 volt from an AC power supply across the primary coil. Now switch on the power supply. What is the brightness of the lamps compared with each other? Now connect the CRO across the primary coil. Switch off the time base of the CRO. Then record the length of the vertical trace on the screen. Keep the Y gain setting unchanged. Repeat the measurement with the secondary coil. Obtain the voltage ratio of the transformer from the length ratio of the vertical traces. Compare the result with the turns ratio. Are they the same? We will measure the voltage ratio of a transformer and compare it with the turns ratio using a voltage sensor. Connect 2 voltage sensors to a data logger interface and then connect the data logger to a computer. This is a simple transformer. Its primary coil has 10 turns and its secondary coil has 25 turns. Connect a 2.5 volt lamp to each of the primary and secondary coils. Then, connect a voltage sensor to each of the primary and secondary coils. Apply an AC voltage of 1 volt from an AC power supply across the primary coil. Switch on the power supply. Compare the brightness of the 2 lamps. Run the data logging program on the computer. Display the voltage recorded in real time by the 2 voltage sensors. Record the peak value of the voltages in the primary and secondary coils. Calculate the voltage ratio of the transformer. Is the voltage ratio the same as the turns ratio?
In the experiment, we turn off the time base to measure the peak-to-peak voltage induced in the secondary coil. Your teacher will show you in the next lesson how to compare the primary and the secondary voltages directly using a double beam CRO. From the experiment, we can find that the voltage ratio and the turns ratio are the same, and thus Vp over Vs equals Np over Ns. And this formula applies to all transformers, even if the efficiency is not 100%. So by adjusting the turns ratio, we may have different secondary voltage for different appliances. Say, when the number of turns for the secondary coil is more than that for the primary coil, the secondary voltage is higher than the primary voltage. This is called a step-up transformer. When the number of turns for the secondary coil is less than that for the primary coil, the secondary voltage is lower than the primary voltage, and it is called a step-down transformer. A multi-tapped transformer may provide output of various magnitudes across its output terminals. What would be that voltage VB? Example 5 on the next page shows the CRO traces of primary and secondary voltages. The solution shows how to calculate the voltage ratio. I would rather turn off the time base and measure the peak-to-peak voltages instead, as the reading error can be reduced. Also, in this example, the voltage ratio Vp over Vs is larger than expected, which means the secondary voltage Vs is smaller than expected. This is due to flux leakage, which means some of the magnetic field lines produced by the primary coil do not pass through the secondary coil. 3. Currents in a transformer. A transformer may change the voltage of an alternating current. Does it mean that a transformer can create energy? The lamp in experiment 6C becomes brighter when secondary coil has more turns. Where does the energy come from? Energy cannot be created. The lamp is brighter because more energy is delivered by the power supply. The energy output by a transformer is exactly the energy input to the transformer from the power supply. If the transformer is 100% efficient without energy loss, then the electrical power is given by power P equals V times I. So the input power V in, I in, which is Vp, Ip. Then the power output is given by V out, I out, that equals Vs, Is. And therefore, Vp, Ip equals Vs, Is. And so we have Ns over Np equals Ip over Is if there's no energy loss. Or Ns over Np equals efficiency multiplied with Ip over Is if the efficiency is lower than 100%. And so you can say the primary current Ip increases as efficiency decreases. On page 300, the circuit shows the effect of power loss in the transformer. However, I would like to amend the numbers a bit for consistency. In the second circuit, the load resistor is identical to the one above, hence of 1.1 ohm. The secondary current should still be 10A, and so the output power is also 110 watts, same as above. The input power is doubled as the efficiency is just 50%, so the primary current is 1A, which provides an input power of 220 watts. So amend the values as shown before you move on. And now you may see the effect of energy loss by the transformer. The primary voltage does not change. The secondary voltage is not affected as it is determined by the turns ratio. The secondary current is determined by the load resistance and thus also not affected. It is only the primary current which is increased in order to provide a larger input power to the transformer so that the load resistor may receive the same power output from the transformer. In example 6, The 24-watt light bulb requires a secondary voltage of 12 volt and also a secondary current of 2A. The voltage ratio determines the turns ratio and hence the number of turns in the secondary coil. Lastly, the primary current is determined by the required input power, 24 watt. The required power will be higher if there is an energy loss in the transformer, and hence the primary current will be higher. Say, if the efficiency is 80%, the input power will be 30 watts. The primary current will be 0.136A, which is larger than the answer in part C. In example 7, the same light bulb labeled 12 volt 24 watt is connected in series with the 220 volt supply and a resistor. In order to provide just 12 volt to the light bulb, much of the voltage develops across the resistor, and hence just a small percentage of energy is converted by the light bulb to generate heat and light, and so the efficiency will be very low. 4. Practical transformers. Designs of practical transformers aim at reducing magnetic flux leakage, resistance of wire, eddy current flow, and energy loss due to continuous magnetization and demagnetization of iron core, as these are sources of energy loss in the transformer. Thick wires are used to reduce energy loss due to Joule heating effect, also called ohmic loss. Soft iron may be magnetized and demagnetized more easily with little heat produced. The core is laminated so as to reduce eddy current flows and hence heat loss due to heating effect of eddy current. In this way, practical transformers usually have high efficiency, mostly higher than 90%. Try checkpoint 5 on the next page, and don't forget to read exam link 1